Hello everyone, welcome back to the Chemical Engineering and Aspen channel. As you know, these days we are focusing on the module of Chemical Reaction Engineering. So in this regard, we are bringing the lecture number 22 for our valuable viewers. So in today's course coverage, we will again be focusing on chapter number 5, which is related to the isothermal design of our building block number 4. And this building block number 4 is based on previous three building blocks, which is mole balance, rate laws, and stoichiometry. And as you know, in our previous lecture, which was lecture number 21, we had started continuous stirred tank reactor calculations. We have seen it for the first order and second order system for a single CSTR. So today we will be moving to multiple reactors, and first we will discuss or derive the relationships for CSTRs in series and for CSTRs in parallel in the second phase. But before going to the derivations, we have to first recall our algorithm, which was mole balance and design equation, rate law, stoichiometry, combine and evaluate all of these. Now, if you see, there are two reactors which are in series. The feed whose concentration, initial concentration is Ca0 with the volumetric flow rate as V0. In the first reactor, the reactions takes place. The rate of reaction is minus Ra1 and the volume of the reactor is V1. Then the product from this reactor goes to the second reactor. Obviously, the product of this reactor will be the feed of this reactor. The concentration is Ca1, the conversion is X1. In this reactor, the rate of reaction is minus Ra2 and the volume is V2, while at the outlet, the conversion is X2 and the concentration is Ca2. So we are assuming that for these two reactors, first order reaction is taking place and there is no change in the volumetric flow rate. So the relationship which we have derived in our previous lecture for the first reactor single CSTR, or we had said that when there are multiple reactors in series, for the first reactor it will be Ca1, which is the concentration of species at the outlet of the reactor is equal to Ca0 over 1 plus tau K. We had said tau K over there, but for the first reactor it will be tau 1 K1, and we had said tau K for the first order system as Damkohler number, if you recall our previous lecture, lecture number 21. So applying mole balance on reactor number 2, obviously we know the conditions for the reactor number 1 or single CSTR, but for reactor number 2 we will have to apply different parameters or different conditions. So for reactor number 2 we said V2 is equal to Fa1, which is the flow rate at the inlet of the reactor, minus Fa2, which is the flow rate at the outlet of the second reactor, divided by its corresponding rate of reaction minus Ra2. Now we know that F is equal to volumetric flow rate into the concentration. So V0 Ca1 minus V0 Ca2, V0 will be common, so V0 bracket Ca1 minus Ca2, and that minus Ra is equal to Kca. So for the second reactor it will be minus Ra2 is equal to Kca2, and accordingly once we rearrange it, we get Ca2 is equal to Ca1 over 1 plus tau 2 K2, and that see this relation is same as that of this, but now there is a change that it is represented for the second system. Now we know the value of Ca1, that is Ca0 over 1 plus tau 1 K1. So what we need to do, we need to substitute that value over here, and accordingly you see Ca0 will be at the numerator, 1 plus tau 2 K2 that will be coming here, and 1 plus tau 1 K1 that will be coming over here. So that is how that equation is represented like this. Now if we assume that both reactors are of equal size and these operate at the same temperature, what does that mean? That tau 1 is equal to tau 2 and K1 is equal to K2, because K is a function of temperature. So accordingly, when there is no change in temperature, the K1 K2 will remain the same. In the same way, tau is equal to V over V0, the volume over volumetric flow rate. We have already said that volumetric flow rate is a constant term, and now we are saying that both reactors are having same size, means the volume is also constant or the same for both. So accordingly the tau 1 is equal to tau 2. So accordingly this will be 1 plus tau k, this will be 1 plus tau k. So accordingly it will be 1 plus tau k whole raised to power 2, Ca0 over 1 plus tau k raised to power 2, that is equal to Ca2 for this system. Similarly, in the same way, if there are n number of reactors of equal size, which are connected in series, and these are at the same temperature, operating at the same temperature, reactor 1, reactor 2 up to reactor N. So accordingly we say it as CaN2 is replaced by N, that is equal to Ca0 1 plus tau k raised to power N. Now you can see this 2 and this 2 are replaced by the value N, or accordingly that tau k, we can say it as Damkohler number. If you remember our previous lecture, that for the first order reactions the Damkohler number was tau k, for the second order it was tau k Ca0, and accordingly we can derive it for the further reactions as well. And similarly that Ca is equal to Ca0 into 1 minus x. So now once we rearrange it, we get x is equal to, in terms of x, is equal to 1 minus 1 over 1 plus dA1 raised to power n. That dA1 is the Damkohler number for the first order system, or we could say it as tau k. And once we further align it, we get the value of x, or minus Ra is equal to k Ca raised to power n, and C a raised to power n is equal to Ca0 over 1 plus dA raised to power n. So that is represented over here, or we can say dA as tau k. So k is coming directly over here, and Can is replaced by Ca0 over 1 plus tau k raised to power n. So this is how you calculate the conversion. Now if you know there are 3 reactors, accordingly you will apply it for the first reactor, for the second reactor, and for the third reactor. In the same way you can calculate the rate of reactions for the given system as well. For the first reactor, simply substitute n is equal to 1 and solve it. For the second system it is 2, for the third system it is 3, but provided that the number of reactors are having the equal size and these are connected in series and having the same temperature in the system. Now if you look at this graph, it's a very important graph once we are talking about the number of reactors connected in series, and you see that it is for the first order system, and there are different values of Damkohler numbers. There are different trends available over here. The x-axis contains number of CSTRs connected in series, while y-axis contains the conversion. Now for the value of Damkohler number as 0.1, you see with the increase in number of CSTRs, there is a continual increase in the conversion. However, if you see at the value of 0.5 or even at the 1, like if only one reactor is installed, for Damkohler number value as 0.5, the conversion will roughly be 30%, or if for value of 1, it will be approximately 50%. But you see, if we have installed 2 reactors, here the conversion will be roughly 18% or 16%. Here it will be above 50%. Here it will be nearly 75 to 80%. So you see there is a huge difference. Once you go to like 12 number of reactors, the value is continuously increasing, but the maximum limit is roughly 65 to 70%, while here it is almost approaching the 100%. But you can see this trend over here. If you see this trend, there is no appreciable change. So you can see that approximately after 5 reactors, there is no significant change in the system, while for high values of Damkohler number, you have to keep it in mind that there is a variation of Damkohler number over here, and we have earlier seen it as well, that with the increase in value of Damkohler number, the conversion increases. So you can see for higher values of Damkohler number, you need less number of reactors in series, while for lowest value of Damkohler number, we need more reactors in series to get the conversion. So that graph is very, very important once you are dealing with the number of CSTRs in series having the same size, operating at the same temperatures. You have derived the relationship. Now you need to know that is the value of Damkohler number, and accordingly you can predict that for the system containing the particular amount of reactors or number of reactors connected in series, what would be the maximum possible conversion that you can achieve, and that with the increase in the value of Damkohler number, the conversion pattern is a bit more achievable, or the more conversion is achievable than at the low value. So now moving on to the CSTRs in parallel now. The previous case was for the series, now it is for the parallel, that this FA0 is now divided into 3 parts. There are 3 reactors connected in parallel now. FA0I, the flow rate is represented as FA0I. For first reactor it will be FA0-1 for the first, FA0-2 for the second, and FA0- for the third. The rate of reaction for the first reactor will be minus Ra1 and the volume will be V1. Like we said, there are I number of reactors, so the rate of reaction will be minus Rai and the volume will be Vi and the corresponding flow rate will be Fa0I. And for n number of reactors, the flow rate will be Fa0n, the rate of reaction is minus Ra and it will be V of n, the volume of the reactor. So accordingly, we can specify this expression, the design equation for the CSTR, as V of I is equal to Fa0I xi over minus Ri for I number of reactors in the system, while x1 is equal to x2 up to xn is equal to x. We are assuming, or we are saying, that the conversion in all of these reactors will remain the same. Obviously, if conversion remains the same, then the rate of reaction will always be the same. Minus Ra1 is equal to minus Ra2 is equal to minus Ran is equal to minus Ra. Now the volume of each individual reactor is linked to total reactor volume, and similar relationship exists for molar flow rates. What does that mean? That V of I is equal to single V divided by the n number of values. That if we want to calculate one reactor volume, it will be the total volume divided by the total number of reactors that are connected in series, and same goes for the Fa0I, that the total flow rate divided by the number of reactors. For example, if there are two reactors, the flow rate will be halved, and in the same way the volume will be halved. Instead of using a single reactor, you have divided it into 2 parts or 3 parts or 10-15 parts. So accordingly, if you see this, if I take you back, Vi is replaced by V over n, Fa0I is replaced by Fa0 over n in this expression. So accordingly, V over n, Fa0 over n, xi over minus Ri, this n is cancelled out with this n. Accordingly, this value is V is equal to Fa0 xi over minus Ri. And we have seen that xi is equal to x minus Ri is equal to minus Ra. Now you can see that this expression has come back to its original state. What does that mean now? That means that the conversion achieved in any one of the reactor in parallel is identical to what would be achieved if the reactor were fed in one stream to one large reactor of volume P. It means that if we installed one single reactor, or if we divide into 3 parallel reactors or 4 parallel reactors or 5 parallel reactors, the overall conversion will be the same, the overall rate of reaction will be the same, the flow rate, if you sum all of these flow rates will remain the same, and obviously the volume will also remain the same. Like V is equal to V1 plus V2 plus V3 up to so on, and accordingly you see that if you consider one reactor or if you consider multiple parallel reactors, the values or the answers will remain the same. The division is done to make sure that it does not occupy too much space or for the operations reasons as well. So that is the representation of or derivations of CSTR in series and CSTRs in parallel. I hope you have understood the lecture. If you have any query suggestion related to this lecture, please provide it in the comment box. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.